Hi, and welcome to another Rigonomicon.com video. Today we're going to be going over quite a bit of material, and we're going to be covering some methods for dealing with roll bones, and or you call them twist bones in some cases. I'm also going to be going over bendy bones and setting up methods for making your character look like their arms are made of rubber. Um, it's going to be a little bit of a controversial video because I'll be talking about, I guess we can call them, let's just refer to them as classic Maya rigs. You can always tell it's a classic Maya rig because there's lots and lots of objects, lots of references, and your hierarchy is quite extensive. And the reason why is because you need to create these extra nodes to zero things out, and you have gimbal controls, things to deal with gimbal, and you have other objects that are there just as references, so you can measure angles between things. Anyways, I'll be going over those methods as well as, let's say, more up-to-date methods with from Autodesk. Like Autodesk, I criticize Autodesk every once in a while, but when it comes to the advancements in rigging, there have been a few things here and there that have made things possible through the new APIs and the Open Maya and all that stuff. And I've been making my own plugins which simplify things and use things that are not Euler. We're going to get to Euler and the issues that come with that in this video quite often, because we're dealing with twist bones and Euler values heavily. And the methods that I'll be showing you for how we can deal with this stuff will include quaternion and transformation matrices, which are much more reliable and give you better results. However, I will be showing classic methods in Maya, so I'll try to cover as much as I can, depending on what kind of setup you have and which version of Maya you have. Some of this will differ a little bit. So let's just jump in there. So I've created this basic setup with skin. And the only thing really that stands out here is that instead of using a traditional Maya joint here, so if I were to put that into a bone, I wanted to avoid this because I started doing this way, and it just gets messy visually. So I added one of my shapes around it and make it a lot easier to use. So let's hide that. But this is, for all intents and purposes, this is a joint, a Maya joint, and that's what the hierarchy is. Now, the only other thing that you need to keep in mind of the setup that I have here is that this mesh has been skinned not to these bones, particularly the ones in the box shape. They have been skinned to this one and to the hand, and they're ready to go. But I've added a couple of bones in here that here I'll show you. So, for example, I have these bones, and the skin has been applied to that, but these are all children. These are all nodes that are children to this node here, right? So if I rotate this bone, the other little bones will inherit that transformation, and this works just like a normal skinned object. It's just that we're going to be using these to do our roll bones. So a roll bone, just to explain, something that spins in order to be able to keep a certain shape. So what is this shape and why do they exist? So I'll just show you real quick a little animation that I have on this hand. So let's say that even though we could do better with the some of this volume, for the most part it's doing what it's supposed to. If we go side to side, it's fine. But when we spin it or roll it, we get this effect, which is commonly referred to as a candy wrap. So this is what we're trying to fix, primarily at the beginning of this video, where we're going to be spending most of our time understanding what the problem is and trying to solve it. So, like I just mentioned, we can create these little pieces that we can then spin to maintain its volume. If you're not familiar with the skinning, the problem with skinning and why this is happening, I strongly suggest going to the basics, the rigging basics that are on the Rigonomicon.com, specifically the skinning one. It'll explain in great detail, painful detail, how vertex values in a linear skin are done, and how it's calculated, and basically the weaknesses of using linear skinning. So this is a result of using linear skinning or linear skin. It can cause these kind of things where you have a full rotation, and all it's doing is linearly blending between the two values, and it can't do anything about it. So by adding more bones, we're adding more values that it can use as a reference. So I can do that type of thing, and then that, and then that. But getting the roll value out of this hand to go into these objects, well, that's a bit tricky, isn't it? So so we're gonna start with the first approach that is quite common, and that's to simply take the rotation value of the hand on the x-axis, just the x rotation, and throw that onto this bone here and make it spin a certain percentage. Okay, so if I go into the editor here, and by the way, you can do a lot of rigging just with the node editor, frankly. There's a lot you can do with this. So if I take this bone, which is going to be my reference bone, or my bone that we're using in order to calculate everything, and I press a little plus sign here, I'm going to have the hand, and we're going to have the rotation values here available, so we can pull them out and connect them to directly to the rotation value of this bone here. And just like that, we're going to create our rig, where you can tell, you see the yellow box right here? That means a value has been connected to it, and that you now, when you see the animation, it works pretty well. In order to get the other ones on top, you don't want to just transfer the value, you want like a percentage of that value. So there's a couple of ways we can do this. And I'm not going to spend too much time doing this. So I'm just going to, I don't know, put it on 2 bones. I think that should be plenty to show the how we do this. So we got this guy, and we're going to need this guy too. Put him over here. So we've got a lot of mouths to feed here. So we need to figure out how to get these values into here so that they work as a percentage. So we're going to need, this is 100%. Maybe this one would be 66%, and then this one's 33% of that value. So in order to do that, we can do I just press tab on the node editor, and then I can do multiply, and we're going to just grab the first, this one here that's popping up, and I can take the rotation value and just put it in here, and it's going to multiply whatever values are here and output it here. So unfortunately, I can't just enter a value in this this node. Like if I'd use the multiply divide node, but that one comes with a cost of, you have to set it to multiply, and then you've got 3 to work with. Anyways, it's just kind of weird. This one, at least, multiply whatever the inputs are, and that's all there is to it. But we need a value to go in here, so I'm just going to type float, and I think there's a constant float, meaning this is just a number. And even in the channel box, I can set that to 0.66. That's fine. It doesn't matter if we're off by decimal. And then that value now, it's going to multiply those two things. So it's going to take 66%. And now this object should be 66% of the rotation. So let's see. So it's rotating less than this one. You can see it. Now we're going to just grab 33% for this guy. Now, this is something you need to get used to. For those of you that haven't felt the pain to be able to copy paste this, you cannot press Control-C, Control-V. You have to press Control-D for duplicate. And that takes a little time until your brain gets used to that. So just thought I'd mention it because, it can really mess up your scene, and then you have to find what it brought in and delete the stuff that got copied incorrectly. So anyways, I'm going to set this to 0.33%, and I'm going to make that the number that's multiplied with the value of the rotate x, and then that's going to connect to the rotation here. So that's going to be a 33%. And already we can see that this is a much smoother kind of like fall-off effect. And just with 3 bones, we're able to get something that looks pretty good. Now, I'm going to close this, and yeah, you can do quite a bit of rigging just with using these kind of nodes. And I strongly recommend getting good with that because it can help you out quite a bit, and it avoids having to create extra objects. That's kind of what I was referring to at the beginning, using those kind of methods, like the node editor has been greatly improved, and there's more of those little nodes that don't show up here because they're not DAG nodes. And you can do a lot of good stuff with that. All right, so let's look at our result here. We've got this rotation. That's pretty good. There's nothing that's breaking. Now, one of the benefits of this method is that because it's using the X value directly, it's not limited to 180 degrees. You can keep, well, if I can actually rotate it more than 100, here, come on, Gizmo. There we go. So it's allowing me to do it, even though I've only got 3 bones to work with. It's still okay. It didn't pop. It's just, it's limited to how much of a skin value. So the more of these bones I have, the better this the better that look will be. But for the most part, I just undid that. This is a very stable way of doing it. And some people would say, well, then that's it. That's we're done. This is good. So here we were starting to see a bit of an issue. Like, look, the minute you pass, because it's a y-axis, the minute you pass a certain value, it's going to have some trouble calculating. And that has to do with how gimbal gets calculated, or Euler values, rather, I should say. So the important thing here of what I'm trying to show you is that this is pretty good because of all the work that we did previously. So if you haven't looked at the videos, like the basics for rotation, if I tell you that a position and a scale has independent components, meaning the X value and the Y value on a position are completely independent to each other, you're probably going to go, well, yeah, no kidding. But then if I told you that's not the case for rotation when there's Euler involved, if you didn't know that, I would strongly suggest looking at the videos related to rotation and gimbal in the Rigonomicon's section under basics, because that is a fundamental thing that we need to keep in mind while we're doing this. And there are, if you follow certain golden rules that I've spelt out, and it's also on the Rigonomicon.com, there's a section called Golden Rules. If you follow those rules, you will avoid gimbal issues quite a bit. And though this has been set up nice and clean, the values here are quite clean, and everything's been aligned correctly, and that avoids a lot of issues. And so we're getting a good result because of that hard work. But even with that, there's still a limit of what we can do. And here I'll show you another scenario where this could be a problem. So I'm just going to create just a locator, and I'm going to just get it so that it matches the position. Also, anything that's on this shelf, you'll find it like in the normal shelves for the most part. I just like having shortcuts for things I use often, and I save a lot of time that way. And if you don't have this shelf, consider getting it from the Bacon Strip webpage, or the Rigonomicon. I'll have a link for it in the Rigonomicon.com page. There's a couple of things in here that you can't even access normally through Maya's UI, but I made it possible for you to be able to access it. A pretty good example is under shapes, there's a parent shape button, for example. And this is something that you quite often hear about. Basically, you can transfer a shape onto another object just by using the parenting command in Maya, but they didn't make a UI for it. So it's there, but you need to have a script to get access to it. So a lot of these tools are just accessing certain features in Maya that you wouldn't normally be able to get to. And the ones that have the BS plug label mean they are using specific plugins that I have written. Anyhow, so with that aside, I strongly suggest getting something like this, or making your own shelf to make things a little bit faster. Okay, so this object was just created, and I matched its location to this object. And now I'm going to make a constraint so that this drives this object, and it's going to ignore the animation that's there. And I'm going to do that by going into the rigging menus, going to constraint, and just setting the orient constraint. In this case, I'm going to set the maintain offset, and boop, and I'm going to click on that button. And so it shouldn't have moved, and now I have something that I can rotate. Now, one of the reasons why I'd said maintain offset on is because I didn't make a match rotation of it. So this is world aligned, and this is This is x-axis pointing to the child node, and so on, using all the rules, right? So you're going to notice that its value right now is not 0, 0, 0, which is what's on here, right? So when you do a constraint, there's always some sort of conversion value. It's going to try to do its best to convert everything to Euler. Like I mentioned before, Euler is very inaccurate. It uses 3 coordinates, and here's the worst part of Euler. You can have 2 objects that have the exact same orientation. They're pointing in the same direction on the whole kit, and they have 2 completely different sets of values. When you can, and that's kind of the reason why the tool in Maya for fixing an Euler problem, when you get a gimbal issue and you gimbal out and you press that button in the in your graph editor, what it's basically doing is it's looking at the key from before and trying to find which of the 2 solutions for Euler is closest to it. And by doing that, it fixes the problem, and then it punches in the other solution. So a lot of times the issues exist because of this inaccuracy in Euler and these problems of dependency between each axis. That it causes a lot of unreliable data, and unfortunately, a lot of the, again, I'll just call them classic rigs in Maya, still use Euler values to drive certain features. And in order to do the tricky stuff that we're going to be doing today, I needed to convert a lot of these values to quaternion, or even better, into transformation matrices. Okay, so all this just to say, this object has values that are different than this one, even though it's constrained, which means there's a conversion factor. So if I do stuff like this, let's see, I go like this, it's fine. And I start spinning it on this, it's good. And if I come back here, I try to do this, eventually, like right now I'm just rotating things. It's doing pretty good, huh? Like so far so good. But eventually it will break, and once it's broken, I can tell you it's very hard to fix, even with the gimbal stuff, because it's trying to find the best solution possible, and this is not a reliable method for rotating your hand. So because of this constraint, you're getting a lot of values. You can see them right here that are changing quite wildly, especially if you do something like this. So this is okay. Like I'm trying to follow the anatomy and try to be fair about this as much as possible. And so far, we can say that it's been pretty good. We've had very little issue, but eventually we will hit that thing, like I mentioned before. There you go. So see, it's just a matter of time. The clock's ticking. So now we have this issue, and getting rid of this, like we found one that's causing some trouble. So fixing this is very difficult. Anyways, point is, and if you look carefully, you're not really far from the initial position, like the initial rotation. So anyways, my point here is that even though this method overall is good, and we reinforce this method thanks to the knowledge we have from the basics of rigging, when we were able to get this to be pretty decently reliable, it still has a lot of issues where it can break, and you're at the mercy of quaternion, or rather Euler issues that can come in here. And maybe I can go into the F-curve editor and change that and fix it. This is not a reliable method, and it's not the one that most people are using. So now I'm going to show you real quick the one that basically everybody uses in most rigs. So if I get close here and bring out these roll bones. Now, there's one of the constraints that gets used a lot for a number of things, and there's a lot of abuse to this one. So we're going to be using the aim constraint, and the reason why the aim constraint is so interesting is that it has that up vector control. So that means you're basically controlling 2 directions. You've got the aim itself, right? It can aim at a thing, and then you've got the roll, or the up vector control, which makes it spin along that aim, which is the quintessential concept of what a quaternion is. You have a direction, and then you have a roll on that direction. For any of you that are interested in that stuff. So an aim constraint would allow us to, and I'm going to set it up real quick here. I'm going to set one up so that it's bad, and then I'm going to make a better version of it quickly. So I'm going to create this object, and I'm going to give it a name so we know what it is. This one's going to be called hand up, and I'm going to copy that, make sure it's ready, because the aim constraint unfortunately still uses naming convention. Anyways, not a problem. So I'm just going to make it match in both. So that way I can then, not both of them. I just want the one object to translate. There we go. That's good. So basically, I'm trying to set this up as the reference for up, meaning this node, which is the one we're going to be setting up, has an aim constraint that points to this hand. So basically, it doesn't move. But what's going to be interesting is that I can set this up to be the up vector, so that this will always match it, so that as I move it, it'll roll relative to it. And if this is attached to the hand, see if I do this. Oops, hang a second. Let me just go. Okay, so I select this and this. Okay, there we go. Nice and easy. I just pressed P and I selected it in the correct order. I selected the child first, then the parent, and pressed P, and it made it select. And again, we have these god-awful lines that connect joints. Real quick thing, the reason why I have these joint nodes with these fancy visuals is because something you might not know is that you cannot include things that are not joints in a skin. So anything that's a skin gets skinned. In even inverse kinematics, you cannot have joints in an inverse kinematic chain if it's not a joint, at least not in Maya. So what I've been doing is I've been changing the visuals of joints so that they can be anything I need it to be. The only thing is, if you don't change the joint visual, you get these lines that show up for any child connections. It's okay. We're going to leave it like that, and it's fine. It's giving us an indicator at least. So this object now is child of the hand. So that means that if it rotates, it follows along, right? So we're going to be using both the hand, its location, right, and this object's location as points of reference. So if I select this hand here, I press Q, so I can get rid of the gizmo, and I can select with the piece, and I select the hand, the joint that's going to be for rolling, and then I go into constrain, orient constraint with options. Actually, it's not an orient constraint. This is going to be an aim constraint. And so let's see here. I'm going to deselect things so we can see clearly what's what. This is the object that we're trying to control. Its x-axis is what's going to be aiming. So I'm going to put aim vector set to 1. I'm going to get rid of the maintain offset. In this case, I just want it to, well, we can leave it on. It shouldn't, if we see values, we'll know just how much of a error there was in the way I set it up. Or how much of a, it's like if I move this thing too far out, it'll be a little off axis, so there's going to be little decimals. Anyways, it's not going to make a big difference. So aim vector is going to be 1, meaning I want it to aim directly at the hand, because it's directly on this. The parent node for this is this bone here. I call it an ulna. You can call it a forearm if you want to. You call it whatever you want. And because I was very careful with how I set my hand, the hand is directly in front of the of this node, so it only has an x value, meaning it's directly in front, and that allows for this constraint to work nicely. So if you don't have that, then you'd have to possibly create another node that is aligned perfectly with the parent, and then create a joint, do an orientation constraint with this node. Anyways, point is, be clean with your joints, make sure they're well aligned, and you can do what I'm doing right now in the video, and it's going to be fine. For the up vector, I'm going to use this object's z-axis, right? So I'm going to set this 0, and then I'm going to make this a 1. So it's going to point to this object on the Z. And I'm going to use, again, I've mentioned this in other videos, these values in a lot of these constraint tools, they're kind of labeled in a way for like the first option, and they don't really make sense for the other ones, but you know that this is going to be the reference. How are you going to do the up vector? We're going to use an object and its transform, its position, basically. And all we need to do is name a thing. Oh, look at that. It's got the same name already, so we're good to go. And basically what it's going to do is it's going to make this z-axis, we said the up vector is the z, it's going to aim at this hand up object. So let's just set that up now. All right, because of the order of selection, we've basically told the tool the first thing I selected was the object I'm going to aim at. Then this is the thing that's going to be modified by that. And then I'm going to use an object up for figuring out where that is. And by clicking it, look at that. The decimals are the really tiny errors. So we did a good job of setting everything up in so that we didn't even need the maintain offset. It would have been fine. Okay, so point is, this object now has, if you can see clearly, the rotate XYZ values are really close to 0. There's some decimals there that are being hidden, indicated by the negative. But for the most part, this is nice, is cleanly set up so that it points to this object. So if let's just test it. If I move it, the object will aim at the hand no matter where I place it. But we're never going to be moving the position, really. So we shouldn't have to worry about that. And then this thing is the thing that is controlling how it'll turn. So if I select this here, and I move it, you'll see that that z-axis is pointing to the object just like we set it up. So now, because this is child node of this hand, as the animation goes, so something happened here. And we're going to talk about that in just a second. It didn't happen over there. Here it seems to be okay. And the roll is working. We have a roll that is working. And now we just got to figure out what's all this about. So one of the things you're going to notice is as the reference node crosses over into the past the aim direction, this kind of stuff happens. So some people, a clever person goes, okay, well, if that's crossing it, if I just move it up, now it doesn't cross. Aha, got it. And then, oops, I forgot. It goes back the other way. So that's going to be a problem. So no matter where you put this one, it's going to cross the line on something simple like this motion. You should be able to go further than that. And even this, you're putting your hand on a table, you should be able to do that no problem, if not more. But here's where I did this on purpose to set it up like this because it's visually easy to understand that this is the up of a hand. So I'm just going to reload this very quickly because at this point there's too many undos. I wouldn't trust it. So, and it's not going to take us very long to set up an object named hand up. Again, I'm just going to bring that over here and where I want it to be. I'm going to show you based on what we just discovered. So I just want to, do that. Now I'm going to move it along this axis. There we go. Okay, a spoiler. Okay, so let me undo that for a second. So basically we saw that this rotation it was the one that broke, but this one was fine. Could be because there's not much of a rotation going on here, but clearly it was because it was crossing the line. You're never going to cross the line if your node is in the front, right? So the solution to this, and this is why most people set it up this way, is that they grab this thing, and instead of using the up vector on the z, they will use this other axis where your rotation here, in this direction, most human beings cannot really bend their wrist in this direction very easily. We all can only do about 15 to 20 degrees. And if you're one of those people that says, oh no, I can do a lot more than that, that's because you're probably twisting your arm and you're actually doing more of this than you are of this. And I can see that all the time with, especially for games that have auto rifles or guns or something like that, where you see the anatomy being broken. They do this kind of thing, and they're like, well, in my reference videos, they did that. If you look carefully, no, they didn't. They were doing this type of thing. They were using more of this motion. And you can just test this yourself. Put your hand on a table and try to make it rotate in either of these two directions. You'll notice that you cannot go beyond a certain point, and it's not just you. Most people can't do that because we just don't have the muscles and the bones for it. Our bones block us from being able to go in any more than that. For the most part, you're going to find the and this is again the basics of rigging. The first thing you animate, right, is the z-axis. So I set it up so that this would be the z because this is where the majority of the motion for that hand is going to be. And my x-axis points to the child node so that I can spin on it like this, nice and clean. So that means I've minimized the use of y so we don't have any gimbal locks as much as possible because anatomy kind of tells us not to do that anyways. So this is a good setup, which means the y rotation is what we're going to be using, which means that that's going to be, if I look at this object here, that direction is going to be, on this case, because this bone is aligned with the parent here, it's the y-axis. And it's going to be, so to make our life a little easier, we could just move this over here so that it's positive y. Right? So it points in the positive direction, so let's just do that. So now this is child of this object. And we're just going to get this to be the driver of this for an aim constraint. Aim vector is still x. The up vector is going to be y. And we're going to use the object as a reference, and we're going to be apply. Okay, we could have gotten rid of the maintain offset. I'm a bit of a nut with that. But anyways, point is, now if we look at our animation, our test animation, we should see that this is the dangerous rotation that could break things. But because of anatomy, we're safe. And generally, people use this as a way of controlling the twist bone. And I've seen a lot of rigs that use that. But like you just saw, there is a weakness to this method, and it can happen in certain cases, and things can break. However, there's the other part of the equation, which is percentages, right? Before we did it with a node editor, you can also, there's a lot of people that do this method for figuring out how to blend for the other bones and using this one as a reference. This is like 100%. Now all the rest are going to be like a percentage of that. And the way you do that is you create another object and you match the one that is going to have the full, like basically that one's been set up with the aim, so that's 100%. Now this one is going to have the same parent, so this is the parent. I'm going to make these little locators a little bit smaller so they don't get in my way. I'm just going to make that a little smaller. And this guy, well, he can be big. This guy is going to, like, let me just press up on my keyboard here. Boom. So that's the parent. And if I look at this node here, it's also its parent. And this is in the same starting point as this one. So this can be used now as a reference for what is 0, meaning no rotation whatsoever, no twisting. And this now is 100% twisting, which means I can grab these two and then select another bone like this one and say, you are going to be some sort of a percentage of both of these. So if I go into constraint, orient constraint, I'm gonna I don't need the maintain offset. I just want pure values from these two anyways, so that's fine. If I set that up now, by default, if I check the, I just select this object, right, which got you can see the constraint. You'll notice that in the constraint section, where it says orient constraint that we just created, it makes reference to the ulna. That's the one with 100% of the rotation for the twist. And then this other one, which I didn't name, it's called locator. So it's set to 1. So if you have a 1 and a 1, it'll basically average, and that means that this is 50% and that's 50%. So, and if you ever have any trouble with that, just if it bothers you, just put 50%, 0.5, 0.5. Now if I look at this, it'll give me a 50% rotation, not 100% rotation like the other one. If I wanted to add this one into the mix, and then make this a certain percentage. So like that's easy enough. You just go how much. This is going to be 0.66, and this is going to be 0.33, meaning it's going to have 66% of the rotation of what's being calculated with the aim. And now this one over here is going to have an opposite setup. So I'm going to have these two like so. Still have this here. Apply. If I go here now, I only want 33% of it, and whatever's left goes to the nothing. And now, if you look carefully, you're going to see that it's doing a decent job, considering there's only 3 bones in this equation, in this setup. We could change it so that the values are a little different. So instead of 0.3, maybe we'll do 0.2, and that's 0.8, and it'll be a little bit softer at the end. And then maybe this guy also would have a little less. So anyway, see, there's all kinds of stuff that you can do. You can change these values to be more linear and so on. And that's how you would control it. That is the classic method of doing this. Then there's variations on this method, but for the most part, you're going to find that this is generally what people do. As you can see, there are some issues with it. So even when you're not rotating, see that little wiggle there? You're not really rolling the arm. I made sure to use just one axis, and somehow that is affecting it. It's not the end of the world. That could happen either way. Let's be honest. And then the other, the roll, it's not bad. It's not bad. It works overall, but we know about that about that issue. Okay, so now I'm going to show you another method of doing this. This is hopefully going to be a lot easier. So if you go, let's go back to a clean scene and bring this up. And we are going to just do this kind of thing. I mean, select this object, and I'm going to grab, I think I have it set up so you can do at least 4, up to 4. So we could just do the first 2. Like I've worked in many places where you only have 2 to work with, and some places maybe you can have a third one if you're lucky enough. Maybe something like this. Let's be fair in comparison to the last method. And then over here I have my constraints, and I have something called bacon roll bones. Now you're pretty much done as far as setting up goes. Most of the work was on setting up these bones so that they have 0 values and they're clean. You're going to notice this is already working pretty well out of the box. So let's give it a try. Let's, as I like to say, kick the tires on our rig. So let's see, can it go on the Z-axis? Yes. Both directions? Yes. Can it do the Y-axis? Yep, that's even doing a little thing where it's banking as you get to difficult places. So that's nice. And the X-axis is good up to 180 degrees, where there's a limit, like right there. Book. I mean, your hand cannot rotate more than 100. There's no way you can rotate your hand. The radius and ulna, it's like 2 bones that are kind of spiraling with each other. There's absolutely no way you'd be able to spin your wrist more than 100, like even more than 90 degrees, I think, in either direction. But let's just say that you can go up to 180 degrees, but not beyond 180. And that's with every system. Pretty much everything has that limit, except for the first one that we used, where it was using the X value directly. But that's that's unreasonable. 180 degrees is fine. And just by zeroing out things correctly, we were able to do that. So for the most part, the reason why this is working, like the way it is, and why it's this stable, and you're not getting anything pop other than the 180 degrees, is because of the math that was involved in doing this. So if I look at this, and I go into the node editor, and I say, okay, show me that bone. So this is the bone, and now I just want to see how it's getting its value. And the answer to that, here's the bone again. This is the constraint, and this constraint is using the hand's values and with all of its Euler values that are eventually being converted into a transform matrix, and then that transform matrix is being sent there. And then we have values from the ulna that's being sent Oh, the ulna is just the scale. That's normal. We don't really need to worry about this guy. But for the most part, it's just a constraint, a reference, and it's doing the rest of the heavy lifting for the rotation. And the thing is, it might be like everything in Maya references an Euler rotation. But what you do with that Euler rotation is what makes the difference. If you use it directly to do your twist bone, then you're asking for a bad time. You're going to have a bad time. If you convert that into a quaternion, or better yet, into a transform matrix, much more reliable math that can give you much better results like you're seeing here. Okay, and also we're not creating any extra reference nodes or anything. There's nothing. It's just a little constraint node, and that's it. So if I close this now, I'm going to show you why that's working and why other systems. Let's say, okay, look, I'm just going to bring this out. That's why I said it was going to be a little bit controversial. So if I load up Malcolm here, and I have him in this pose because I want to show you this part. You see this thing coming out of his wrist? It's not a squirrel trying to escape his wrist. It's an issue with the twist bone. At first is what I thought. So there's some sort of issue here. But what's actually happening is in order to get these nice clean shapes so that when you go to extremes, it pushes out like a little, it has a blend shape basically to keep these nice shapes, and it activates it based on values from the rotations, but it's using the Euler values almost directly. It's making reference nodes to get to it, but that's where the math will break eventually, and you get this thing where you get a bad Euler value that kicked in, and then book, it threw it to the blend shape, and then this happens, and you're going to see it. It's in a number of places. It's unfortunate because it has a nice twist value here for the rest of the arm, and that if your other systems are using the Euler values, then things are going to break. And here's another thing. I'm just going to press Shift and then this to open up the menu, the root, and look how long it took. I clicked on the root node and it opened up the hierarchy, and that's because, oh boy, it's so big that's off the screen. We're going to need a bigger outliner to see it all. And I did a check before, and it was close to 2,000 nodes. That's without seeing the shapes, right? This is just straight up DAG nodes. You can check it here too. It's like, oopsie, I meant that, DAG nodes. So if you look carefully, you're going to notice that each object that's in this rig has so many parent nodes. And the reason why is because some of these are for helping you with gimbal locks. Some of them are for zeroing out values. Now here's the thing. Autodesk did make an update recently where it has now the parent offset matrix. So zeroing out objects have never been easier. You can now zero out position and rotation on any object. And that's not something we had before. And before we used to have to create extra objects to zero out their translation if it was a joint. Also, you may not know, like I may have mentioned this at the beginning, where the joints are the only thing that you can use in a skin, and they're the only things that you can use in a hierarchy for IK. So there's a lot of issues of using joints in the past that you had to work around, and these are some of the workarounds, right? So all of those things add up to lots of extra little nodes, which means there's thousands of objects here, and you have blends between multiple setups. It's painful to fix things like this. If something goes wrong, this is really difficult to fix. So I'm not calling out the Malcolm rig in particular. There's a lot of other rigs that do exactly this, and I would say that this is very much an approach that has been as a classic approach in Maya. Okay, but Autodesk has been making it possible for us to avoid using these methods. So let me go back to what we were doing. Okay, so now we have this. We're back to this, and I'm going to show you how much we can abuse transformation matrices and quaternions and still have a coherent, functioning, reliable rig. I'm going to add roll bones on top of bendy bones, on top of an IK that is stretchy. That's like that's a pretty tall order, and we're going to see just how many nodes got created for this. So first, maybe let's solve all the bendy bones. So if you don't know what a bendy bone is, it's very simple. If you select any object in this current setup that I have, you can move these bones around, and you could create like these soft shapes or these bendy rubbery shapes, and you can even rotate them to better get the thing that you want. And it's still these are child nodes, so you can always keep your IK working, so it's fine. And I've seen a lot of rigs that do this where you manually have to do this, and it's not a big deal. It's not so bad. And there's a couple of them that even do some automatic macaroni shapes for you, so you can have tension and so on. It's not bad, but you still lose that hands-on control with, like, let's say a Bezier. Bezier, you can control just a couple objects, and you'd be able to make them stick to the path. So here we go. In this setup, I'm going to unhide the Bezier objects that I've created. Now, already you're thinking, well, we were just talking about thousands of objects. How many objects are here? Well, let's be honest. That's it. That's not much to deal with here. What are these objects that I've created? Even though there's tons of bendy bones, it's something that Malcolm didn't even have. And then there's these objects. What are these objects? So if you've ever used a Bezier control before, which you probably did when you were in the F-curve editor or the graph editor, basically the idea is simple. For every key or starting point, you have an object that controls the starting point, and then you have these tangents that are going to control the curvature, and then you have an ending point, or another, in the case of a graph editor, another key. And I do that again here. So you have starting point, ending point, and two tangents in between to control the curvature between those 2 points. And I'm going to use that to control these values here, these bones here. So all I'm going to do is I'm going to select them in the right order. So then I'm going to select these objects in the order that I need them. And I'm going to run this the bendy bone setup. And that's it. You're done for the setup for that. And what it does is it allows you to use Bezier controls to distribute these bones that are been added. And the nice thing about it is they're still part of their child nodes of this. So it's very, you can still animate normally. You could add, in this case, I would make this child of that bone right there. So for example, this, instead of being child of this node, I would make it child of this node, simply put. And now everything works the way it should. There you go. That's very much the setup that you could have. And now I'm going to run this also over here. So starting point, first tangent, second tangent, ending point. And then in this case, we have less bones to work with. We don't need that many. Constraint, bendy bone. And let me just check it. Sure enough, everything's good. Okay, so that's good. So we got our bendy bones, and this will allow us to create all kinds of interesting things. So we can even detach these, and it will follow along, and you'd animate these things. So you have a lot more control with this than you would with the other setup. And doing this manually would be kind of painful. And you can control the just by changing the distance, you can control how close they are to each other and so on. So that you already have a pretty good setup for bendy bones. Now the other thing here is that this object over here, when you rotate it, has a built-in twist action. However, just like we talked about before, this needs to turn based on this object. And we've gone through multiple methods, so we've learned that the best method is using some form of quaternion-based roll. So I'm just going to select, well, first of all, I'm just going to double check here. I think, yeah, I need to freeze this object for rotation. So I'm just going to go align, freeze 0 to joint orient. So now that's been zeroed out. I think it's something that I forgot to do beforehand. So I'm just going to set that up now book. Everything's been frozen. Everything's back to normal. And now my starting point is 0. That's important for a twist bone to work. I did it cleanly before, but this time I forgot to do it for this one. But anyways, it's good to show this stuff. Nothing. Sometimes things don't work out the way they should. And in this case, it's just that it's a thing that we need to do. That is a good reminder for anybody watching the video. Always zero out everything that you can before setting up your rig. Now all I'm going to do is do that the bacon roll. So now this will spin automatically based on its value. So if I look at the original animation that I had, it's doing it correctly. It's doing the spin. Now here's the fun part, right? Regardless of like if I do something like this, something crazy, okay, this will still be coherent and it will rotate along its own axis. So as it spins, first let's grab this guy and make sure it's not connected to the hand or to this object. I'm just gonna make it child of this bone. Now when we get to that, see, it stays, it has the shape, and we can do something that is very difficult to do normally. And this would break, if you were using Euler values, this would break instantly. So let me just undo so we can get back to the original shape. Okay, so now what I'm going to do is I'm going to add an IK to this. So I'm just going to select the hand, and I'm going to hit Constraint. I'm going to use the special one that I have. Like normally I use the Maya one. In this case, we're going to use the Bacon IK because it has a built-in stretch tool, and it will allow us to do this. Let's see here. There's an up vector. Might be causing some trouble. There you go. It's just not in the right place. But we could get that under control. But the point is, now we can do this kind of thing. For the most part, that's working. Maybe one of the things I would do is make this the endpoint go to where this is, and I'm going to be, yeah, let's do that. So if I go over here and I select this hand, and then I select this endpoint, I should be able to create a constraint, a point constraint, and apply. And now this object will be following that object. So now if I just grab this, I'm going to close this. If I grab this and pull, it's going to stretch with it. So one of the criteria for a bendy, for a roll bone, is that this has to be, the roll bone has to be child of basically the arm, which is over here now, and not the hand itself. So I couldn't just parent it to that because all roll bones are always, their parent is the same as the hand or the thing that you're using as a reference parent. That's all. You can switch it up with, like, let's say the shoulders. I've written something that does the equivalent for that over there, but since we already set this up to be like a normal roll bone, we now have stretchy IK with Bezier, so we're able to control things quite well. So I can do this kind of thing, type of deal, and it's going to follow the tangency of that curvature. We can do some crazy stuff with this. And it doesn't matter where you are in space. The Euler, it doesn't have any Euler anything. Everything is using more modern methods. I keep mentioning that because it is the key to be able to do this kind of abuse. Like at this point, we have roll bones, and oh yeah, it got reparented. So I'm just going to parent that there. So now if I turn this, the roll bones are working just fine on top of the bendy bone, on top of a stretchy IK. This is a lot of abuse right here. So we're doing all of that, and it's still functioning as designed, and we don't have a gazillion objects in here. We just have a handful of things that are very easy to understand what they are. If things break, we can go directly to the bone and inspect it through the node editor and see exactly what's going on. So all this to say that if you're building your rig with a more classic approach, you may have you might hit some ceilings of what you can do, and things will not work well when you start combining them in particular. And in this case, I just showed you three completely separate systems that don't seem to fail, and they're working simultaneously together. And that's good. So okay, so I think that covers everything. I just want to say that this is not. I'm not calling out any particular rigs. I mean, a lot of rigs use that other method, and that's okay. But I would strongly suggest looking into these methods and building, either using other plugins like the ones I have, or making your own. You'd be surprised how easy it is to do that. There's a lot of documentation for, especially if you want to go pure Python, you could use API 1 and 2 from Autodesk. I won't go into detail what those are, but at the moment you can use that if you want to. You can use like the ones I've been making, which are C++, and you get a lot of benefits from that too. So anyways, point is, the newer methods are very reliable, and everything can work well together, even in complex scenarios. Hopefully this has helped you for setting up your twist bones, and hopefully you can use these plugins wherever you are. If not, I have shown you other methods that are more traditional, and they seem to work as well. So all good. All right, that covers this video.